the rest of fire science is built on what we cover in the next 2 weeks. So this is kind of foundation. So if you've heard some of this before, good. This just reinforces what you know. If this is new to you, then please try and make sure you get the hang of this, because everything that follows after this is kind of built in these foundations. So today I'm going to be talking about basic fire chemistry. I may branch off occasionally, but mostly chemistry. Next week, basic fire physics. Again, we may do a few detours, but we'll get there. So, if we'll go on to the next slide. Come on. I like it. So we're at week 2. We've had the introduction. We're at week 2 basic fire chemistry. I've actually, one of the joys of writing lectures only a couple of weeks ahead of actually delivering them is that I get to change my mind about the order of things. And so November 12th was supposed to be compartment fires. I'm actually bringing that up. So after we've got the basics, I'm going to throw you right into the big picture of compartment fires, and then we'll kind of work back from that rather than building up to it, which had been the way that certainly Guillermo Rain taught this class last year. That seems to make a bit more sense to me, where we've got some idea of where we're going. So the running order that you saw last week has now changed. Probably I'll change it again before we get to the end, but we'll see. So the basics this week, the next week, and then on to compartment fires. So, fundamental question, what is fire? Anyone care to answer that? What is fire? It's orange stuff, or red stuff, or...
Chemical reaction.
Yeah, I mean, I've got that on the screen. It's physical processing and chemical processes. There's a lot going on. I mean, if you remember back to the candle flame last week, there's an awful lot going on. But one of the things that, one of the concepts that people very often bring out very early in a fire science course, and this one is no exception, is the concept of the fire triangle. In order to get fire in any circumstances, you need 3 things present. You need, obviously, fuel. You need something that can burn. If you don't have fuel, no fire. You need some oxygen. It needs to burn with. And you need some heat to get the thing going and to keep the fire sustaining. So that's the classic fire triangle: oxygen, fuel, and heat. Because obviously, if you take any one of those away, take away the oxygen, you've still got heat and you've got fuel, but it can't burn, so the fire is smothered. Other things may still go on. You may have fuel and heat. It may be pyrolyzing, maybe producing smoky stuff, but it's not actually burning if there's no oxygen. One of our PhD projects a couple of years ago looked at an instance where it was a fertilizer material that was burning. I'll use burning in inverted commas. The problem with that was, even though it was an oxygen-starved environment, the oxygen was part of the chemical that was burning, smouldering, combusting in some way. Oxygen was built in. So even though, if the fire brigade had got there and blocked out the oxygen flow, it didn't matter, the thing just kept going because the oxygen was built in with fuel. But in general, oxygen is something separate from the fuel, and so oxygen is required. So if you take oxygen away, fire smothers. Similarly, if you've got a fire and you can cool it down sufficiently, take the heat away, you quench the reaction. The fire goes out. You've presumably noticed like CO2 fire extinguishers on the walls around the buildings and so on. Almost everywhere you go you'll find a CO2 fire extinguisher. Do you know how a CO2 fire extinguisher works? It tries to get rid of the oxygen by diluting it. It also tries to bring a cooling effect because the compressed gas is very cold. And you get almost as much cooling effect as you get the starving of whatever the word was I used a minute ago, to get rid of the oxygen, smothering. So you've got both effects, cooling and smothering, to get rid of a fire. What by itself, a CO2 fire extinguisher probably can't do only one or the other. It needs both actions to go together to actually work. And if you're ever in the chance to, if there's a fire somewhere and you see a CO2 fire extinguisher, if the flames are higher than that, don't even try it, because you won't get anywhere with it. In fact, even that is probably a bit big. Flames so high, CO2 fire extinguisher is probably not good enough. I learned that the hard way in the lab a couple of years ago. So the third one, obviously, if we take fuel away from our triangle, nothing to burn, fire is starved, That probably makes perfect sense to you. So, in fire safety engineering, the aim is, if you're trying to deal with a fire, if you can remove one of those, perfect, the fire is out. But the sort of next effect is if you can even just control one of them to a certain degree, you have some degree of control over the fire. If you can restrict, if you have an oil tanker on fire or something, and you can somehow restrict the amount of fuel that's being released from the tanker, you can restrict the fire size. If you've got a fire in a room, and you can restrict the amount of oxygen getting into that room, you restrict the fire size. If you have a fire going on in a room and you can get something cold in there, you can bring the fire size down, you can restrict the fire size. So if you can control any of those three elements, you can control the fire. And that brings me to one of the most fundamental things. If you take nothing else away from this lecture, you might pass the exam, but please take this one away at least. Every time, and I mean every time I ask a question involving fire in a tutorial or an exam, ask yourself 3 questions because they all will be important. What is the nature of the fuel? What do I know about it? How does it burn? What is the chemical makeup? Ask yourself about the fuel. Ask yourself, how is the air moving? Especially when we come to the scenario of a compartment fire and you've got the airflow is almost certainly constricted by the doors and windows. If you know what the air is doing, you know something about how the fire will behave. So how does the air move and where does the heat go? If you're dealing with, again, a compartment, the heat goes up, it hits the roof. What does it do then? Does it accumulate there? Is there a mechanism to take the heat away? Is there a chimney? All these things will affect how a fire burns. So every time you face a fire problem, whether in this course or anywhere else in the future, ask yourself these 3 questions. And if you come up with a good quick answer, that will give you a good direction to go about how addressing the question. Because if there's an obvious way the heat is going to go, then you know something about how the fire is going to behave. If there's an obvious oxygen source, or an obvious way that the oxygen is restricted, you get a good handle on the fire problem. So every fire problem, I can't stress that too much, every fire problem, ask yourself 3 questions before you do anything else. Now, as I said, we're talking about chemistry this morning, so if you ask a chemist what is fire, not a chemist that like dispenses you drugs, you know, a pharmacist, but I mean, I've asked someone over in the Department of Chemistry, School of Chemistry, what is a fire? They might tell you it's an irreversible exothermic oxidation reaction. And if any of those words scare you, because you've not heard them before, then listen carefully, because we'll hopefully unpack them. Is anyone unfamiliar with any of those words? No. Good. Yeah.
Like, for oxidation, we have always H2O, right?
You have always
H2O.
H2O being produced. In general, yes. I'm trying to think if there's any exceptions to that. I mean, oxidation generally means that the reaction uses oxygen. So oxygen is required to promote it. It's also to do with changing electron states, but we don't need to get into that. So H2O is probably always produced, but there's probably an exception I can't think of at the moment.
But like when we're burning a gas,
Yeah.
it's not oxidation. It's not oxidation. Like we don't have H2O when we're burning like a gas, for example.
When you burn, like what?
Like I don't know.
I'll not answer that. I think I'll probably answer that question in a minute. So we'll come on, but I think you may be confused slightly, but we'll come back in a moment. So it's irreversible. It only goes one way. Once you've set fire to something, you can't turn it back into what it was before. That's basically all the irreversible means. If you light a candle, you can't then go and get all the bits of soot and recombine them to make the candle again. It doesn't work like that. It's a one-way process. Exothermic is it gives out heat. Oxidation is it uses oxygen. Also, in the technical term, has something to do with electron states, but we're not going there. And it's a reaction in the broadest chemical sense. It has product, it produces heat, it produces particulate smoke, and we'll get back to the particulate smoke more later, and gases. So, in general terms, we need fuel, oxygen and heat. Through the reaction, the arrow always in chemistry terms represents the reaction, comes to products. So products that are gases, products that are solids, products that are heat. Very, very occasionally produces solids products that are liquids. But those are rare cases. So for the moment, I'm just assuming it goes to solids, gases and heat. So in very general terms, a chemical reaction, I've designated the reactants, the things that activate before the reaction, as Ra and Rb. These go through the reaction and come out as products, product C and product D. Now we also have relative quantities of all those things. So we've got a quantity A of reactant A, a quantity B of reactant B, producing a quantity C of reactant C, of product C, and a quantity D of product D. And obviously, this is a very idealized scenario. It may be reactant A, reactant B, reactant C, reactant D, reactant E, produce products F, G, and so on. I'm not saying every chemical reaction is two reactants and two products. For those of you that haven't studied for those of you that have studied chemistry, do you remember the concept of a mole? For those that haven't studied chemistry, do you have any idea what a mole is? Shake your heads now. There's a couple of people at the back shaking heads. A mole is a measure of the quantity of a chemical that's not dependent on the mass, it's not dependent on the volume, it's entirely dependent on the number of molecules. So if you have hydrogen gas, it's very light, it weighs 2 atomic units. A mole of that is 6.02 times 10 to the 23 molecules, comes out as being 2 grams. Whereas if you've got something like carbon dioxide, it's much heavier. Brain, something goes away from me. It's 16, 22, it's 40-ish, 44. 44 atomic units. So a mole of that is 6.02 times 10 to 23 number of molecules, but that'll be a larger mass. It'll be 44 grams compared to the 2 grams of hydrogen. So if you know what the chemical weight is of a molecule, and you multiply that by 6.02 times 10 to the 23, you get the number of grams that 1 mole of that molecule will weigh. For those of you that haven't done any chemistry, I'm assuming you're vaguely familiar with the shape of a periodic table. You've seen these boxes with letters in it and numbers. You'll often find that, you know, it'll have a carbon in it and it'll say 6 and it'll say 12. The 12 is the atomic weight, not the atomic number. The atomic number and the atomic weight are different. And it's always the atomic weight that we are concerned with. So if you look at a periodic table and you look at the numbers and it goes 1, 2, 3, 4, 5 as you go from box to box, and it doesn't have any other numbers, those aren't the numbers we're interested in. Those are the atomic numbers. You need to find out the atomic weight of each element of each molecule. So, yeah. If you're still in a mystery about what a mole is, please go and read Wikipedia tonight, read a book, talk to someone that's done chemistry, and get your head around that, because when we come to balancing reactions, which is what most of the first tutorial, or the first half of the first tutorial that you'll have to hand in, all hangs on your ability to balance reactions, which I shall explain over the next few slides. So, for example, propane. Propane is C3H8, 3 carbon atoms and 8 hydrogen atoms in 1 molecule. Reacts with oxygen in a certain quantity to produce carbon dioxide and water. That's a fairly straightforward chemical reaction. And we've got these 4 quantities, A, B, C and D. Now you can work out, and this is one of the tasks that you'll be doing for the tutorial, in order to balance that equation, you basically count the number of C's on each side of the equal sign, count the number of H's, count the number of O's. They must add up. So for that, in this case, for propane, 1 propane molecule, C3H8, requires 5 O2s to complete the reaction, and the reaction goes to 3 CO2s and 4 H2Os. So that's 1 mole of propane requires 5 moles of oxygen for the complete reaction, producing 3 moles of CO2 and 4 moles of water. Water in that sense, it doesn't produce liquid water, it will produce water as a gas, water in the gaseous phase. So as I say, we're generally assuming that the products are gases, not liquids. Now if you note, we're starting off with 6 moles of reactants, and we're actually getting 7 moles of products. So the number of moles on one side does not necessarily equal the number of moles on the other side. It's the number of atoms that need to sum up. So in this case, there's 204 grams on each side of this equation to balance it up. There's 3 carbons, 8 hydrogens there. We've got 60, it all balances out. So heat release during burning in terms of this kind of reaction is expressed per mole. Sometimes in textbooks it's also expressed per gram. So you have to be careful what the units are. Make sure if you're doing a calculation that's in moles that the number you're using is kilojoules per mole or joules per mole, not kilojoules per gram or per kilogram. And this reaction is a perfectly balanced reaction. If you had that just the propane and just oxygen, nothing else there, in a sealed vessel, that reaction goes smoothly like that, and you get the heat of combustion is the energy that's released by that reaction per mole is 2044 kilojoules per mole. That has a negative sign on it. Why does that have a negative sign on it?
Releasing.
It's releasing, yes. This is where chemists and engineers argue, because approximately half the time in engineering you'll see that with a negative sign, and the other half of the time you'll see it without a sign at all, because it's just an amount of energy being transferred. And it doesn't matter to the engineer in one level which way the energy is being transferred. The chemist is really concerned that the reaction is losing energy, and so from the reaction's point of view it's a loss of energy. But the engineer might just think it's a transfer of energy, and actually I'm more concerned about what the vessel's getting, and the vessel's seeing positive energy. And so be very careful whether it's plus or minus. Most times when you're doing a calculation it's really obvious which way it goes. But there are very small occasions where sometimes you add things up and the numbers just don't work because you've got multiple reactions going on at once. And you think, actually one of them should have been minus and was plus, and the other way around. Of course, except for pure chemicals, it's impractical to work in units of moles. I mean, if I'm burning a sofa, what is 1 mole of a sofa? It's a meaningless concept. So we tend to, as engineers, convert things to grams or kilograms. But watch out, always make sure what the units are. I mean, I'm sure it's the same in almost every class you go to. Watch what the units are, because if you start using the wrong units, everything gets mucked up. So if we're talking about reaction rates, we've got this general equation. Reactant A plus reactant B in various quantities go to produce products C and D. We may also talk about concentrations of reactants. So the concentration of RA I call CRA. And so you've got a rate, a reaction rate, as a change in quantity of the concentration of RA per unit time, per unit volume. For that reaction, of course, because these things work A, B, C, D, you can balance it up to the rate of consumption of reactant A is equal to A over B, the proportionality between the two, times the rate of consumption of reactant B. Similarly, again introducing a minus sign here because we're actually creating product C, but the rate of production of product C equals minus C over A times reactant, the rate of consumption of reactant A. So in the lab, when we're doing experiments, we can actually record CO, CO2, and O2 levels, so we can see in all our experiments the rate at which oxygen is being consumed and the rate at which carbon dioxide, carbon monoxide are being produced. We also have other kit that we don't really need to get into in this course that can measure other things. We can look at production of other chemicals as well. In gases, it's kind of harder to quantify soot, but we can quantify that by shining a laser through it and just looking at the obscuration. But in the lab, we can record rates of production, rates of consumption, and make inferences about the material. So when we burn things in the lab, one of the things I can do is estimate the heat of combustion of the material very easily. And we can calculate other quantities on the basis of these rates. Reaction rates are generally of the form reaction rates is related to some factor K times the concentrations of A of the two parts to the power of their relative proportionality. Have you come across Arrhenius type equations like that in various courses before? Where K is some factor, some constant A times E to exponential to the minus E over RT. Does that look familiar to anyone? Yeah, does that look completely unfamiliar to anyone? Most of you think you've seen it somewhere before. Just some things to note. It's exponential regarding temperature. There's temperature in there, and E is a measure of energy. So it's something to do with, this is called the activation energy. And so as, again, if you vary the temperature of a reaction, it'll go faster. If you get a fire going and you can get the heat up, the reaction goes faster. The activation energy is more down to the chemistry and doesn't change so much. But bear in mind, on any reaction, there's a dependence in temperature. So again, it's the same thing. If you can cool the reaction down, you slow the rate right down. Just a very basic chemistry concept that we may as well cover in passing. Two kinds of reactions. As I said, fires are exothermic reaction. The opposite are endothermic reactions. They're ones that take in energy as they go. So we have, imagine we've got our propane gas and our oxygen mixture. It has a certain amount of energy built into it at this level. The products, carbon dioxide and water, are down here. But the two products don't just spontaneously collapse down to carbon dioxide and water. We need to put some energy in to get the reaction going, and that's the activation energy, so that's the initial hump. So if we raise the energy by introducing an ignition source or heating it up sufficiently till it gets to the peak of the hump, then the reaction will just follow down the hill and lose energy to produce the products. The other kind of reaction is an endothermic reaction, where actually the products, the energy level of the products is less than the energy level of the reactants, but you can't, if you put enough energy into that, you can drive the reaction that way. That actually, it doesn't really come into play at this stage in the course, but as you go on and find out about things like how fire retardants work, generally they're mixing different chemicals in there so that some reactions are exothermic, but some are endothermic. Some reactions are actually sucking energy out, again to have the effect of cooling the fire, to remove heat, to cool the fire, to slow the reaction rate. And so when we come to considering suppression effects, certainly with retardant chemicals, which is something we don't get into today, then we need to understand what an endothermic reaction is as well. Here's our example case. Propane, C3H8, requires 5H2O to go to the products. One thing you find is that if you go to different textbooks, you see different numbers for what the heat of combustion actually is, delta Hc, the heat of combustion. The number I quoted in the last earlier couple of slides back was 2044 kilojoules per mole. But some textbooks will quote that as 2220 kilojoules per mole, which is a higher number. The difference between those two numbers is whether the water comes out at the end of the process as a liquid or a gas. Because obviously water, when it's a vapour, essentially loses energy to come back down to a liquid. So again, there's more energy lost as the water comes down from gas to liquid. If you imagine, I'll take it the other way, you've got water, you need to put energy in it to boil it. When water vapour, steam, comes back down to being a liquid, the steam itself is losing energy. It might not be energy we can use or recover, but the energy is being lost, which is why the heat of combustion in many tables, especially ones devised by chemists, who bring everything back to essentially room temperature values, or standard temperature and pressure as they call it, actually 0 degrees C is where they bring it back to at 1 atmosphere pressure. And obviously liquid at that state, water at that state is a liquid, and so that the extra heat of vaporization is taken into the calculation. And so again, be careful whether the products are liquids or gases. Actually, I've got some tutorial questions here to hand out at the end. And as I was doing it and practicing and looking at the tables, one of the questions that when the table I looked at gave the answer for producing a vapor, water is vapor, and the other one for a different reaction gave it as producing a liquid. So be careful, always make sure you know what you're dealing with. Generally speaking, in fires, you can assume that water stays as a gas, and so the heat of combustion for propane will take the lower value, because wherever the water is when it cools down, it's probably somewhere else in the system and not where we're considering a fire. You know, the smoke goes up, it's got some water vapour in it, but it's outside the windows and gone away or up the chimney before that water cools down. And so in terms of our interest, which is the fire, liquid water is not playing a part. So generally speaking, assume that the lower value if you've got an option, because one probably involves the heat of vaporization. Why delta HC is negative, I asked you a minute ago. Another important question here or another important concept is the concept of stoichiometry. Has anyone not heard the word stoichiometric before? Good, we're ahead of the game now. Stoichiometric is a big word with a simple concept. It just means that that reaction is balanced. That many moles of propane require exactly 5 moles of oxygen for the reaction to be perfectly balanced. That equation is stoichiometric. If we had more oxygen or less oxygen, yeah?
Sorry, just go back to the last thing you said. You said you take the lower value. Is that as in ignoring the negative side, or the lower value because it's more?
It's the lower absolutely nothing to do with the negative sign. I just mean
So it would be 2040.
take the 2044 rather than the 2220, because we assume that the cooling of water happens in someone else's reaction. It's not happening where our reaction is going on. Someone else can deal with the outs. You know, that's probably in the domain of the atmospheric scientists by then. It's not in the domain of the fire scientists. So yeah. So in terms of stoichiometry, that's a perfectly balanced equation. There's an exact, it's not a 1-to-1 correspondence, it's a 1-to-5 correspondence, but that's what you need for the reaction to go perfectly. The question is, what happens if there isn't enough oxygen? And in most cases of fires inside buildings, that is exactly the case. Very soon, if the fire gets to be big, there is not enough oxygen. Suppose for the propane there's only a 1-to-3 ratio, what happens? Half the answer is already on the screen. What happens? You get extra products, you get carbon monoxide. So that's a different balance. So instead of being 3 and 4, we need to rebalance that equation. Just to mention, you can talk about this in terms of being fuel rich, as in the mixture here has got more fuel than there is oxygen, or you can talk about oxygen lean, because it's got not enough oxygen. I'm going to say, please don't talk about it being oxygen lean, because that gets confusing if you do. Always, if you're talking about something being rich or lean, talk in terms of the fuel. So this is fuel rich, there's essentially too much propane, there's too much fuel compared to the stoichiometric reaction. If we had too much oxygen, that would be fuel lean. Because one thing, you start getting to the point where people talk about this and they start dropping the word fuel, so they'll simply talk about a rich mixture or a lean mixture. And if you're in the bad habit of talking about relative to oxygen, you start talking about different things with different people, and it gets confusing. So please, stick to convention. If it's a rich mixture, it has too much fuel. If it's a lean mixture, it has too much oxygen, or not enough fuel. Okay? And this leads us to the concept of an equivalence ratio. As I say, perfect combustion of propane requires a 1 to 5 balance. But if you had butane, it would be a different balance. Yes?
Is there something missing from that equation?
Sorry?
That equation just there. Is there as well, the bottom one. Because how on earth do you balance that?
Jesus Christ, man.
I'll come to that in a couple of slides' time.
Smart.
Yeah, this is an example chemical reaction that goes for like half the lecture, so we'll be okay. So, equivalence ratio is something that fire safety engineers talk about, and probably nobody else really does. But it's a ratio of ratios, which does get a bit confusing, but it's just to balance out. Propane should be a 1 to 5 ratio, but we talk about the equivalence ratio of 1 to 1 fuel to air for the stoichiometric mixture. So we need to divide the actual ratio by the stoichiometric ratio. So for propane, it should be, stoichiometric ratio is 1 to 5. And in this scenario that we're considering is 1 to 3, because we've only got 3 oxygen to the 1. So 1/3 divided by 1/5. We've got an equivalence ratio for this equation of about 1.67. And as I said, if the equivalence ratio is greater than 1, it's fuel rich, or simply rich. So rich is more, you've got more than 1. If it's fuel lean, you've got less than 1. That's how you remember which way around the equivalence ratio. Because it's a ratio of ratios, it's easy to get confused as to what goes in the top and what goes in the bottom. But if you remember that if you've got more than 1, you're rich, then that's important. You're richer rather than poorer. So anyway, balancing that equation. All chemistry is actually a 2-step process. If you think about what happens in the first step, we're taking the reactants and breaking them apart by putting in the energy, and then recombining them. And chemistry always recombines them in the most energetically favourable way. So, if we've broken this up into, imagine we've broken it up into discrete carbon atoms, hydrogen atoms, oxygen atoms. The reality, nature, call it what you will, wants to get the most energy out of that it can. So it recombines them. Now what we find is that the combination of hydrogen and oxygen gives out more energy than the combination of carbon and oxygen and 2 oxygens, which gives out, again, more energy than the recombination of carbon with 1 oxygen to give CO2, or carbon to give solid carbon soot. So because life wants to extract and wants to suck the most energy out of it, water will always be preferentially made. So if there's a possibility that the reaction can create water, it will create water. So H and O and 2 H's and O will always combine to make oxygen, rather than those oxygens going to combine with carbon. And wherever possible, carbon and 2 oxygens will combine to make CO2, rather than carbon and oxygen making carbon monoxide. And wherever possible, the reaction will try and make carbon monoxide rather than soot. So these are giving out less and less energy as we go down the list. So that when we come to balancing, so we talk about preferential reactions. The one higher up the list will happen preferentially to the others. So when we're coming to balance this equation, first thing you do is work out how much H2O can I make? Because as much H2O as we can make will be made. So we've got 8 hydrogen atoms on this side. In order to have 8 hydrogen atoms on that side, we want to have 4 H2Os. How much oxygen does that take? That takes 2 of those. No, that takes 1. No, it takes 2. It takes 2 of those 3 O2s out of the equation. Because we make all our water up using all the hydrogens and as many oxygens we've got, and then we look at what we've got left. We've got 1 O2 and 3 carbons. How do we balance that? And I hope I do that in the next slide. So in the next slide, yeah. What might happen is the middle, the possibly, it is balanced if we just assume we have no carbon dioxide produced. So propane and 3 oxygen produces 3 waters and 3 carbon monoxides and no CO2. That balances. Yes?
That's not balanced.
Is it not? No, it's not. You're right. No, hang on. You're right.
Can't balance it. Unless
All right,
unless
yeah.
you're right as well, or you half the C3.
No, I've balanced C3H6, haven't I?
Give that man a Nobel Prize.
Yeah. You're right. Okay, well spotted, thank you. I shall correct this before it goes on. Before it goes up. Okay, you can't balance that one. Thank you. Has everyone else realised what my mistake was? No. I've got 8 hydrogens on this side, but I've actually only got 6 on that side. It's not balanced. And you're right, you can't balance it, because if you had 8 hydrogens on this side, you'd have to have 4 H2O, and you wouldn't have enough to produce the 3 CO there. So we would be producing carbon solid soot. Or, possibly, you get the scenario here where I've actually reduced the number further. You might just get to a situation where there's no combustion. The reaction simply might not work. So I need to introduce at this point the concept of a flammability limit. It's not like every mixture of propane and oxygen burns. It doesn't. If you have 99% propane and only 1% oxygen, obviously, there's not enough oxygen to burn. So that can't work. So if we consider flammability limits, if we have an air mixture, because generally we're talking about burning in air, burning in pure oxygen is a different scenario that we maybe get to later. There's some bounds of percentage of the fuel in air, and we're talking about gaseous fuel here, percentage of the fuel in air that it will burn. So if we're talking about methane, for example, anyone have any idea where in that scale methane burns? If I've got 50% methane and 50% air, does it burn? I'm getting a few heads shaking. No, it doesn't. If I've got 2% methane and 98% air, does it burn? A couple of people nodding heads. Actually, no, it doesn't. With methane, it's approximately 4 or 5% to approximately 15%. So if you've got more than 15% methane mixed with air, it doesn't burn. Even though there's fuel there, there's not enough fuel to keep the reaction going. The reaction would be too cool and it just wouldn't sustain. Similarly, if you go the other way, you've not got enough fuel to keep the reaction going. So methane is in that range there. Propane, what do you think? Propane, is it coming down the scale or going up the scale? Up? You think you can get more propane? Hands up for ups? Hands up for downs? Hands up for I have really no idea? Okay. It's actually down. Because per mole, there's an awful lot more to burn. So we need more oxygen to burn propane than we needed to burn methane. So actually it slides this way. And as you increase the alkane size, if you increase the size of the chemical, you've got petrol, octane, decane, that sort of size of thing. It comes further this way. One huge difference, carbon monoxide really wants to burn. Carbon monoxide, if you've got that even up to about 74% carbon monoxide in air, it will burn. But down at the lower limit, if you've only got 10%, it probably won't, because there's not enough of it there to produce the heat to keep the reaction going. Because carbon monoxide burning to air actually doesn't release a lot of heat relative to other fuels. The biggest span of any chemical that we're interested in is hydrogen, which goes from 75% hydrogen in air will burn down to about 3 or 4% hydrogen in air will burn. And when I say burn, it doesn't just go bang and that's it gone, or it might do, but you can, if you've got it in those quantities, it will sustain burning. But I must stress, this is at ambient temperature. Remember the 3 questions I asked at the start? What's the heat doing? What's the fuel doing? What kind of fuel is it? What's the oxygen? We haven't considered heat in there. Things change as you change temperature. So if I take these exact same reactions up to elevated temperature, what do you think happens? The limits shift. Do you think they shift wider or do you think they come narrower? Wider. Anyone think narrower? Good. Percentage of fuel in air, we've got lower flammability limits, upper flammability limit. As you increase the temperature, the bands widen. So 15% methane in air burns at ambient temperature. But as you increase the temperature, you can get to the state where 20% methane will burn in air if it's hot enough. Similarly, increase the temperature, you may be able to get it down to the stage where 3% methane can burn. We also, it's worth pointing out that somewhere about the stoichiometric ratio, somewhere in the middle of the flammability limit, so you've got the right amount of air balanced with the right amount of fuel, and you heat it up far enough, obviously you get to the auto-ignition temperature. You don't need a spark or a pilot flame to get it going. The thing just goes spontaneously, because you're putting enough energy in terms of temperature to reach the activation energy. But as you notice from the shape of the curve, as you tend towards the flammability limits, the amount of energy you have to put in them, you have to raise it to a higher temperature to get auto-ignition as you tend towards the limits. So yeah, I just said that. It requires more energy to ignite a mixture that is close to either the upper or the lower flammability limits. So you do find some graphs in the literature like this. This is the spark energy required to ignite a mixture of methane air for various methane percentages. We've already established that methane flammability limits are 15, where I've drawn the red line, down to about 5, where I've drawn the green line. But even within that range, you need different amounts of energy to ignite different mixtures. And so, round about here's the stoichiometric mixture. It needs the lowest amount of energy to ignite it. As we go away from the stoichiometric mixture, you might need a different amount of energy. That may seem almost completely irrelevant to you in terms of what you're thinking of doing in life. But actually, if you get into something like explosion investigation, starting to work out spark energy and what was it that brought, we know there's a mixture of something flammable and oxygen. We know, generally can sort of reconstruct how fast the oxygen is leaked into the tank, or how fast the fuel is leaked into the room, or whatever it is. We can generally reconstruct what the ignition source might be, and sometimes it is just a tiny electrical spark. And so you need to work out at what point in the development of the incident does that spark energy, is it enough to ignite the mixture? And so if you get into explosions or explosion investigation, that is something that you'll come back to again and again. The other thing I've said here, just as we increase the size of a molecule, so as we go to heavier and heavier fuels, alkane chain length is just simple hydrocarbons are called alkanes, composed entirely of carbon and hydrogen, and the generalized chemical form is Cy to the H2Y plus 2. So there's always 2 extra hydrogens on either end of the chain, if you imagine it that way. But as you increase the size of the chain, what you find is the flammability limits drop. So the flammability limits for petrol, which is somewhere around 8 or 10, it's a mixture, but somewhere around 8 or 10, are probably only somewhere in the range from about 2% to about 5 or 6%, compared to methane that goes up to 15%. So bear in mind flammability limits shift depending on what the chemical is. One thing that I'm just going to mention in passing, you may come across the concept of hypoxic air fire protection. Anyone heard of hypoxic air mixtures? A couple of nods, but mostly shakings of heads. Hypoxic air is a suppression possibility. It is, I know, a few places in the UK that actually use hypoxic air for fire prevention. Basically the concept is if you reduce the amount of oxygen in the air to about 15%, we can all still breathe. If the air is about 15%, we can breathe, but fire can't be sustained. Almost all fires, if you imagine fuel being brought into the mix, almost all gaseous fuels have an extinction point somewhere about 15% oxygen-nitrogen balance. So if you have an atmosphere that's 15% oxygen and 85% nitrogen, I physically couldn't light a match in this room. If I had a cigarette lighter, it wouldn't work. The spark would be there, but it wouldn't be enough energy to ignite the fuels being released. And so I know in London of some sort of computer server rooms. Computers are hot things, they generally carry valuable data, depending on which bank or whoever has the system. And I know at least one bank in London that has a hypoxic air system preserving its computer records. Because even if you get an electrical overheating, there's no way that can lead to a fire, because there's simply not enough oxygen to sustain it. But the technicians can walk into that room, do things, walk out. You know, you've got an airlock on there. Hypoxic air works simply by changing the parameters of the atmosphere to play with the flammability limits. There are very few typical fuels that will burn in hypoxic air. Having said that, there are some, if you've got a material that has oxygen built in as part of its makeup, like alcohol even, alcohol actually can burn in there. It doesn't burn very hot, but it can do it, because it's got some oxygen already built in there. Just on the 15% balance, you can burn some alcohol. If you bring it down to 12%, you can still breathe, just alcohol can't burn. If you bring it down to 10%, we faint. So hypoxic air has actually been suggested for a lot of crazy scenarios as a perfect fire suppression technique. It works best in sealed environments where the atmosphere can be regulated. It doesn't work very well, but has been suggested for environments whereby they can simply flood a space. If a fire is detected, they flood the space with extra nitrogen to dilute things. The window of opportunity between making people faint and extinguishing the fire is so narrow that you've got to be a very good engineer to get it right. And most people aren't willing to make that call. So anyway, just mentioning that in passing. Have all of you seen a Bunsen burner burning at some point in your life? You recognise the two sort of discrete modes of burning of a Bunsen burner. Not a great picture on my part, but you know. Bunsen burner has a gas flow coming in and has a little hole here at the bottom of the main tube, which can either be opened or closed, or in some circumstances put halfway. If the hole is open, obviously air is coming in here, it's entrained in by the gas flow. It mixes with the gas as it goes up, so when it reaches where the flame is at the top, we get a blue flame. Whereas, if the hole is blocked on this side, the gas doesn't get any oxygen until it gets to the top. We get a yellow flame, an orange flame, the gas and oxygen mix as they burn. That is, in very broad terms, the distinction between the two types of burning. Diffusion flames and premixed. Premixed, obviously, where the gas and the fuel are mixed beforehand, you know. before the fire they're mixed. Diffusion flames is not quite as obvious a word to use. There is a good reason for it we'll come back to. Where the gas and the air mix as they burn. So, just a question, how hot is a Bunsen burner flame? Bunsen burner, I'm assuming it's just a methane flame. Methane plus 2 oxygen balances to 2 waters and CO2. You'll note, myself, I've done it, I've dropped the minus sign without even thinking about it. Delta HC for that reaction is 800 kilojoules per mole, or about 50 kilojoules per gram. Should technically have a minus sign, but you know. Now, if we assume for a moment no heat loss, make an adiabatic assumption. So all the heat from that reaction goes into the gases that are produced. That, very approximately, is the temperature of the flame. So I need to know what the heat capacity of the CO2 is and what the heat capacity of water is. So I know how hot they get for how much flame. But we can do this sort of calculation. So I'm looking at temperature rise, which is basically the heat produced by the reaction divided by the heat sink of the products, the amount of heat that the products can take on. So if we plug the numbers in, bearing in mind that we're dealing in kilojoules here, so I need to multiply it to make joules so everything balances out nicely. We've got 2 waters, that's the heat capacity of water, plus 1 CO2 heat capacity of water, gives a flame temperature of 5,852 degrees C. Does that seem reasonable to you? A little bit in the high side? Yeah? So what have I forgotten to include?
Vaporization of water as well.
Vaporization of water? No, I've actually included the vaporization of water in there. Nitrogen. Always remember, although it doesn't take part in the combustion reaction, nitrogen is always there, approximately in the proportion of 21% oxygen, 79% nitrogen. So for this equation, we've got about 7.5 moles of nitrogen there as a product. It's unchanged by the reaction, so we need it there at the end. So we need to include the heat sink effect of the nitrogen. And if we do that, we come out with a number for this flame, for the pre-mixed flame, of about 2,000 degrees C. Does that sound reasonable for a blue Bunsen flame? Still a little on the hot side. But remember, I'm using an adiabatic assumption, so I'm assuming no heat is lost to anywhere else. No heat is lost to the environment, no heat. Actually, in a Bunsen flame, do you know why, when this is a premixed flame, we've got premixed gas here, do you know why the flame doesn't happen until the top? Why does the flame not propagate down inside the tube? Why does the flame not come to this point here?
Isn't it because of the steel pipe?
Yeah, but what's the steel pipe doing?
It's a heat sink.
It's a heat sink, exactly. So what happens is the top of the steel pipe is cold enough, it quenches reaction. And because it's taking away the heat. So obviously, I'm making an adiabatic assumption here. I'm assuming that heat loss is not there. So we've lost some heat at the very top of the pipe already. So in reality, the flame temperature of the blue flame is less than that. But we're in the right ballpark. So, quick tutorial question. I'm going to hand this out. Hang on, hand. Yes.
Why do we have like exactly 7.5 nitrogen?
It's not exact. I was approximate because approximately these should be in the oxygen and nitrogen. And generally speaking, we assume it's in the ratio of 21 to 79%, because that's what it is in the air. But because this is not, I mentioned this is it's not a precise science. You're never going to have exactly perfectly balanced things when we're talking about fires, because fires are messy things. So I tend to round things off. And I can't remember if I said this last week, but when it comes to the exam, if you're doing calculations, I'm quite happy for you to put lots of decimal places in. If you come up with an answer that's 7.543, and actually put that as your final answer, I'm not going to believe it, and I might even take the other point off. Round it off to 7.5, because that's the level of accuracy that you can get in any of these calculations. You know, round it off to nice round numbers that you can work with. Because in reality, I don't know, we've been breathing in this room for the best part of an hour now. You probably find that the amount of oxygen in this room is now very slightly less than 21%, because we've been breathing. It's probably a bit more carbon dioxide. You can't be precise about, you know, it is 21%, it is 79%. So everything has error bars on it, so don't be too precise. Then again, precision is sometimes nice, but when we're dealing with, we're aiming for ballpark figures here, so I'm using ballpark numbers. So again, we need to also think that's a temperature difference. If we're assuming ambient temperature is 20 degrees, obviously we need to add 20 onto that number to get our final number. That's the adiabatic assumption. I've got some tutorial questions I'll hand out here at the end which test you on that. In fact, I put some of these on the screen. This is exactly the sort of thing that I'll be asking in the tutorial. For this week, there'll be something related to this for the hand-in. There's a good chance that there'll be something related to that in the exam. I haven't written the exam yet, so I don't know exactly what's in it. I will know by next week because I've got to hand it in Friday. But so that's, if you look back at past papers, almost all of them have something that kind of relies on these sort of concepts. But of course, real fire, the adiabatic flame temperature of a Bunsen flame, assuming no heat losses, is somewhere in the region of 2000. In reality, if you stick a thermocouple into that flame, you'll find it's probably closer to about 1500. So actually, when I say the error, there are error bars in that. There's error bars of about 25% in that calculation. It's quite significant. But the diffusion flame is colder again. It's about 900, maybe even less than that. Because there's other processes going on that take heat out. There's heat losses. There are more heat-losing processes going on there than in that scenario. The difference between premixed flames and diffusion flames is basically that. Fuel and air mix before they burn in premixed. Fuel and air burn as they mix with a diffusion flame. So in a premixed flame you can get a perfect correspondence of gas to oxygen mixed up nice. You can get a nice stoichiometric ratio, or you can work out the flammability limits. In a diffusion flame it's much trickier because the mixing happens all in one. So actually, as you go through that flame, there'll be different mixtures. You'll have some parts that are better mixed than others. It's a very messy process. That's why it's a lot cooler. Just this briefly before I go for a short break. I think I introduced the concept of heat release rate last week, but just to say, for a diffusion flame, heat release rate, Q, with a dot on it. Are you familiar with the terminology with a dot on top of something? Which the dot means what? It's a rate of change, yes. It's a rate of change of heat. Or it's a rate of release. In fires we tend to think of as a rate of release of heat. So HRR, or Q, very occasionally you see it written as RHR, the rate of heat release, as opposed to heat release rate. But people are different. So for a diffusion flame, heat release rate is proportional to the rate of supply of the gas. If I put more in, the heat release rate goes up. But for a premixed flame, as the flame's burning, the heat release rate is entirely dependent on the area of the flame front and the burning velocity. So if we imagine this room was filled with a premixed gas-air mixture and I lit it there, what you get is the flame front goes out, it goes out spherically, it goes out in all directions. So obviously your area, your burning surface area, is increasing in spherical coordinates. So the area of the flame front gets very large, very big. The burning velocity is the rate at which it goes, which is more or less constant, with some variation. But what you find with a premix flame, generally speaking, the rate of heat release, you get all the heat released very quickly. It's usually much, much higher than the heat released in a diffusion flame. And premix burning in a confined space will lead to an explosion. Because all that heat is given out, you get a sudden increase in volume of the gases, or if there's boundaries, you get an increase in the pressure. Generally speaking, it's enough to blow out windows, doors. If we had a premixed gas explosion in here, not only would we probably lose all the windows, we'd probably structurally damage some of the walls, depending on what the mixture was. So you get a creation of pressure. Actually, that's an experiment that I was involved with a long time ago. There was a premixed gas-air mixture it was a flat but round vessel. It's not one of the pyramids underneath it, that's just the shape the vessel was in, so we could track the edge effects as the explosion went down there. And you can see how it basically is going out spherically. That's actually just in the process of transitioning from an explosion to a detonation. And I might come back to that in a few weeks' time, just what a detonation is, because they're fascinating things. But bearing in mind, if we're talking about an explosion, if you're an investigator, you need to, there's a house exploded, we know that methane was involved, or we assume that methane was involved, natural gas release. We can generally do this sort of simple calculation using the ideal gas law that I hope you're all familiar with, PV equals nRT. We know for methane air the initial conditions. We know initial pressure, we assume atmospheric pressure. The initial volume, we know what size the room is. Initial temperature, we can assume or calculate it. Here I'll assume it's 293 Kelvin. We know if it's a balanced stoichiometric thing, we know what the number of moles of reactants we have. So that's what the N comes into, the number of moles of reactants. N2 is the number of moles of products. In a methane air explosion, these numbers are exactly the same. In other things, they're not. So if we calculate the adiabatic flame temperature, we know what the energy release, we can calculate the final temperature. If we know the final temperature, we are assuming the volume of the room doesn't change significantly, we can calculate the final pressure. Are you with me in that? Again, you can practice this for the tutorial, which gives you a handout in a minute, or at the end. But we can calculate, on the basis of methane air stoichiometric, that it actually, because we're considering constant volume, the volumes cancel each other out. We don't actually need to know what the volume of the room is for this calculation. But if we just assume the volume remains the same, we can calculate that in this case, the stoichiometric, with a stoichiometric mixture, the overpressure is about 8 times, it's 8 times more than atmospheric. And so, if you imagine the pressure in this room suddenly went to 8 times what it is at the moment, you can imagine why the windows would be blowing out and walls would be getting damaged and so on. Anyway, I'm going to take a short break now. I'm going to go to the lab and get something. What I'm going to go and get is a small tin filled with methane gas. It has a hole in the top and a hole in the bottom, which will be covered when I bring them in. Then I'll uncover them. I'm going to hold a match to the top. So you've got 10 minutes to have a break and discuss what you think happens next when I do that.